Hello and welcome to the session. In this video we'll discuss about singular value decomposition. Singular value decomposition is also called as SVD. Now it's a very popular method which is used in linear algebra. It is used to decompose a matrix into three simpler matrices, thereby making it easier to analyze and manipulate the data. The main applications of SVD is it helps in simplifying the complex data into three smaller parts. Especially SVD has a lot of applications in machine learning. Since in machine learning we'll be working with lot of complex data, therefore application of SVD will help us to uncover the hidden patterns and relationships between data, thereby making it easier to analyze and work with large data sets. SVD has a lot of applications in machine learning, like it's used in recommendation systems, it's used for data compression, it's used for finding the important features or feature extraction. It is used to make the data more simpler and more manageable. Now mathematically, if we apply SVD on a matrix A which is of size m cross n, then the matrix A will be decomposed into three different parts: U matrix, sigma and V transpose. So here U is a m cross m orthogonal matrix whose columns are left singular vectors of A, and sigma is a diagonal m cross n matrix containing singular values of A in descending order. V transpose is a transpose of n cross n orthogonal matrix where the columns are right singular vectors of A. So what you have to note here is SVD is just used for decomposition of a matrix A into these three different parts, and you have to note that U is actually the columns of U will actually contain the left singular vectors of A, columns of VT will contain the right singular vectors of A, whereas sigma is actually a diagonal matrix which contains the singular values of A. So let's see a simple what are the simple steps to perform singular value decomposition. So let's say we are doing singular value decomposition on a matrix A. The first step is we have to compute A cross A into A transpose. A is the original matrix, so find the transpose of A and multiply that with A. That would be the first step. Second step is we have to find the eigenvalues for this A into A transpose. Next you have to find the right singular vectors, that is the eigenvectors of A transpose. Next you have to find the left singular vectors, that is a matrix U, and then we have to find the final SVD equation U sigma V transpose. So we will see through the form of a problem in the next video on how we can apply SVD on a matrix A. Now coming to the applications of SVD, as I told you, a lot of applications it has. One important application is, apart from machine learning, you can also use SVD for in digital signal processing, where you can use it to analyze the signals and filter noise. You can also use SVD for image processing. It is used for image compression, it is used for image denoising. Thereby SVD is basically helps in reducing the dimensionality of image data, but yet it preserves the most significant singular values and discarding the rest of not very significant values, and therefore it's a very effective method for reducing the dimensionalities. The other two methods also we have discussed in the previous session: PCA, that's principal component analysis, and LDA, that is linear discriminant analysis. This is the third one, SVD, which is also very commonly used for dimensionality reduction. So in the next session we will see problems on how we can apply SVD. So before we do the problems, just a quick discussion on one of the concepts which I will be using in the SVD problem. When we are applying SVD, we will also be introducing using one concept called as row echelon form, where in one of the steps we'll be reducing the matrix to a row echelon form. So just as a prerequisite, I will be introducing row echelon form in this video. So a matrix, in one of the steps when we are applying SVD, we will be reducing the matrix to row echelon form. Now how do you say a matrix is in row echelon form? Is it has to satisfy these three important conditions. The first condition is in a matrix all the non-zero rows should be above and all the zero rows should be at the end of the matrix. That is first condition. Okay, all the non-zero rows should be at the above in the matrix, and all the zero rows should be below the non-zero rows. The second condition is the first non-zero entry. So you are having a non-zero row. Suppose the first non-zero entry in that row, non-zero entry, in the sense not zero, non-zero entry, we commonly call it as a leading entry, or we call it as a pivot. Now that should always be to the right of the leading entry of the row above it. So basically like a staircase it will be. So non-zero, the pivot should always be to the right of the leading entry of the row above it. The third condition is all the entries below the leading entry in each row are 0. Okay, all the entries below the leading entry in each row are 0. Anyway, I will be discussing this concept again when I'm working on problems. So let's meet in the next session where we will discuss on problems on SVD. So kindly subscribe to the channel, please share it with your friends, and please comment, please write your comments, give your feedback. Thank you so much.